Now the polarization is given by this equation, where n is the total number of atoms, p is the dipole moment, and this is the Langevin function, and this Langevin function is given by this. So I can write it here. It is equal to cotangent hyperbolic A minus 1 over. Now I'll consider a special case. I suppose that when A, which is supposed to be PE over KT, we make a supposition that A is equal to P over KT. Now when A is much smaller than 1, what it means? This implies that if this is much smaller than 1, this implies that this PE, dipole moments time electric field, is much smaller than KT. Or that is, at high temperature and small electric field E. Like when temperature is very high and the electric field we applied is very small, then in that case this A will be very much smaller than 1. If A is much smaller than 1, then we can write this condition that the product of dipole moment time electric field will be much smaller than this factor. Now I have to solve this Langevin function for this condition, that for high temperature and small electric field. Now the Langevin function is equal to cotangent hyperbolic A. Cotangent hyperbolic A is basically cos hyperbolic A over sine hyperbolic A minus 1 over A. Now cos hyperbolic A can be written like this: e raised to power A plus e raised to power minus A divided by sine hyperbolic A, which can be written as e raised to power A minus e raised to power minus A minus 1 over A. Now this is exponential function, okay, and we can expand the exponential function by this series. Our exponential function can be written like this, like e raised to power A will be equal to 1 plus A square over 2 factorial plus A cube over 3 factorial plus up to so on. And similarly e raised to power minus A, which is equal to 1 minus A plus A square over 2 factorial minus A cube over 3 factorial plus up to so on. So if I replace this exponential function by their respective series, and if I put it here, then we have this Langevin function, which is given by e raised to power A. E raised to power A is 1 plus A plus A square over 2 factorial plus up to so on. And then we have this plus sign here, and then we have e raised to power minus A, which is 1 minus A plus A square over 2 factorial and then minus so on, divided by e raised to power A. So we have again 1 plus A square over 2 factorial plus up to so on. And then we have this negative sign, and then we have e raised to power minus A. So instead of e raised to power minus A, I will write this one. So it's 1 minus A plus A square over 2 factorial minus so on. And then we have minus 1 over A is this one. Now if I solve this and neglecting the higher order term, neglecting the higher order term, because A is much smaller than 1. So if I take the fourth power of A, then this will be approximately equal to 0. So that's why we're neglecting the higher order term, like the term including if a raised to the power 4, n, a raised to the power 5, and a raised to the power 6, and so on. So if I neglecting the higher order terms, then I left with, now look at here, this plus a cancel with this plus a, minus a. Now we left with 1 plus 1, which is equal to 2. And then we have this one, a square over 2 factorial, a square over 2 factorial. So we have 2 times a square over 2 factorial. Now next we have, here we have a cube over 3 factorial, and here we have minus a cube over 3 factorial. So they will cancel with each other. So next we have a4 over 4 factorial, a4 over 4 factorial. So we have to neglect the a4 terms now. So we left on only these 2 terms here. Similarly here, this plus 1 cancel with this minus 1. So here we left with plus a, and then minus into minus a is also equal to plus a. So we have 2a. And next we have a square over 2 factorial, and here we have, if I multiply this minus here, then we have minus a square over 2 factorial. So this 2 will cancel each other. So here we left with plus a cube over 3 factorial, and here we have plus a cube over 3 factorial, because this is minus, 1 minus is there. So this minus multiplied by minus is plus. So we have plus 2 times a cube over 3 factorial. And then we have this minus 1 over a. While rest of the term, we neglect them. We neglect the higher order terms. So we left on only these 2 terms. Now here we have 2 and 2. 1 plus a square over 2 factorial. And here we have 2 into a plus a cube over 3 factorial minus 1 over a. This is the Benjamin function for special case. Now next I have to solve this. I will take 2a common, so here we left with a, and here we left a square over 3 factorial. So this 2 cancel with this 2. So we get 1 plus a square over 2, because 2 factorial is equal to 2, divided by, here we have a, and here we have 1 plus a square over 3 factorial is basically equal to 6, and we have minus 1 over a. Now if I multiply, if I take a into 1 plus a square over 6 as LCM, so here I left with 1 plus a square over 2, and then we have minus 1 minus a square over 6 here. Now this plus 1 cancel with this minus 1. So we have this Benjamin function is now become equal to a square over 2 minus a square over 6 divided by a into 1 plus a square over 6. So here if I take in the numerator, if I take 6 as LCM, then here we left with 3a square minus a square. And here if I take 6 as LCM, then we have a into, I can take it like this, 1 plus a square over 6. Now in the numerator I left with 3a square minus a square, and I bring this 6 in the denominator, so here I left with 1 plus a square over 6. If I solve this, we have in the numerator we have 2a square divided by, in the denominator we have, if I bring it 6a into 1 plus a square over 6. So if I further solve it, we have 2a square divided by, If I bring this 6a inside this bracket, so here I have 6a, 6 cancel with 6, so plus a cube here. This is the Langevin function. Now this a cube term, it's because a is much smaller than 1, so we have to neglect this a cube term also. So a cube term will be approximately equal to 0, so we neglecting a cube also. Then we have this Langevin function, which is equal to a square over 3, a over 3, sorry, because if I neglect this one, so here we have 2a square over 6a, so a cancel with this a, so here we left with a, and the denominator we have 3. But a is equal to pe over kt, so if I put it here, then this Langevin function will be pe over 3 kt. So if I put it here in this equation, the polarization, which is equal to np times Langevin function, which is pe over kt. So the net polarization is np square p over 3 kt. This is 3 kt. So this is the polarization of dipolar orientational polarization. Now we also know that polarization is equal to n times alpha d into e, where n is the total number of atoms, alpha d is the polarizability of depolarization, and E is the electric field. If I compare these two equations, let's say this is equation A and this is equation B. Comparing equation A and B, we have n alpha d into E, which is equal to np square E over 3 kt. Now E cancel with E, N cancel with N, so alpha d will be equal to p square over 3 kt, where alpha d is the polarizability of dipolar polarization. So this was all about dipolar or orientational polarizations. Now, when a material is dipolar, ionic, dielectric, like the material, dielectric material, which consists of ions as well as polar dielectrics, then we have all the three types of polarization present in that material. Like we have electronic polarization also present, once we apply the electric field. We have ionic polarization, and we have the dipolar polarization. Like once we apply the electric field, the atoms inside the ions, they get polarized. So we have the electrons move in one way, in one direction, and the positive nuclei move in the other directions. So we have the electronic polarizations. Now these are ions, so it means that After applying the electric field, the positive ion and the negative ion, they also get separated from each other. So we have electronic polarization here, and we have ionic polarization, and also the material is polar material, so it means that the dipole moment also align itself in the direction of electric field. So we have dipolar polarization also there. So the net polarization will be the sum of all these polarizations. So the net polarization or the total polarization will be equal to electronic polarizations plus ionic polarizations plus dipolar polarizations. And we know their values because electronic polarizability is equal to E square over m omega naught plus ionic polarization is equal to E square over m omega naught into 1 over m1 plus 1 over m2, and we have dipolar polarization which is equal to p square over 3 kT. So this is the net polarization present in dielectric material. But remember that the dielectric material will be consist of like ions, and the ions are the molecules are also have a permanent dipole moment. Then in that case the total polarization will be this one. So this is all about polarizations. In the next video I will discuss about some materials like ferroelectric materials, and we have ferroelectric materials, and then we have different kinds of materials. I will discuss about that in the next video. Thank you.